Hello, my name is Yana Rios,
And I'm Amanda Diaz.
and we're going to be presenting our project Picture Proofs. Pictures can be confusing to a reader when trying to understand a concept. Even though the majority of the time pictures tend to help in a problem, they can also lead to false results, being to the fact that we won't understand the pictures completely.
As the saying goes, a picture is worth 1,000 words. In any subject, pictures can help someone understand the concept of a problem. Especially in mathematics, pictures help students better understand what is trying to be explained by words. But if a picture is misleading, the whole concept of learning the right way will be wrong and eventually lead to getting false results for the whole problem. For this project, we will mainly be doing two proofs, one that requires algebraic calculations and a picture, and one only that has picture proofs. Then, based on those two proofs, we will compare and determine if the calculations are really necessary to understand a proof or we can do it just by pictures. Finally, we will look further into other picture proofs for two other equations. We will be focusing on the Pythagorean theorem. The way that works is you need to have a right triangle. What makes a right triangle is a 90-degree angle. To find the hypotenuse of a triangle, which is the side across from the 90-degree angle, you will use this equation, a squared plus b squared equals c squared. Given a and b, you will be able to find the third side.
The Pythagorean theorem went through many different names and diagrams before resulting in the one we all use today. It was named for the Greek mathematician and philosopher Pythagoras. He founded the Pythagorean School of Mathematics in Crotona, a Greek seaport in southern Italy. Although he is credited with the theorem, it is likely that the Babylonians knew the result for certain specific triangles at least a millennium earlier than him.
The Pythagorean theorem is in a right triangle, the lengths of the sides of the triangle satisfy a squared plus b squared equals c squared, where c denotes the length of the hypotenuse and a and b denote the lengths of the other two sides of the triangle. We're looking at three different proofs: a direct proof, a way of showing the truth or falsehood of a straightforward combination of established facts without making any further assumptions; proof by contradiction, an indirect proof established by assuming the opposite proposition is true and that the assumption leads to a contradiction; and proof by cases, a proof where the statement is split into cases and each case is checked to see if the proposition holds.
We can prove that a squared plus b squared equals c squared. Look at the picture below. As we notice, we have four right triangles that are A, B, and C. The total area of the square can be expressed as A plus B times A plus B. Now, looking at the small square, we can say the area is C squared. Given the small pieces, the triangle has an area of A times B divided by 2. And since we have 4, we can say it's 4AB divided by 2, which will equal 2AB. With that being said, the total area will be 2AB plus C squared equals 2A plus B times A plus B. After that, we can expand the A plus B to equal A squared plus 2AB plus B squared equals what we had from the smaller pieces, C squared plus 2AB. From there, we're going to solve for C squared, subtracting 2AB from each side, giving us the A squared plus B squared equals C squared, which then we have proved that A squared plus B squared equals C squared. Now, given numbers, we can show the same equation is true. Here we have A equals 3 and B equals 4. Once we plug them in, we get 9 plus 16 equals C squared, which it will equal 25. Then we solve for C and will be the square root of 25, giving us 5. With that, we have the A side equals 3, the B equals 4, and the hypotenuse equals 5.